All right, so we've done this with 2 dimensions. I want to look today at applying this to 3 dimensions. And the nice thing about this, guys, is that the process that we're going to use is virtually identical to the process we used when we had 2 dimensions. Okay? The difference is simply that we now have a z component and z coordinates to work with here. Okay? So, as we look at this situation, you notice we're not given a word problem at this point. We're simply given, a problem to solve. But it says here that the coordinates of the foot of the perpendicular from the point 3, 0, -1 to the line with parametric equations x equals 2 plus 3t, y equals -1 plus 2t, and z equals 4 plus t. All right, so we're trying to find the coordinates of the foot of the perpendicular. All right, so we have this point, we have this line. So they're kind of prepping us for part B, finding the shortest distance from the line to the point by getting us, first of all, to find coordinates for this foot of the perpendicular. All right, so let's think about this for a moment. What did we do first when we had a line and we wanted to get the shortest distance? We wanted to find that perpendicular. Okay, here's our point. What did we do first? Come on, look at your notes from yesterday if you don't remember. What did we do first when we were trying to find the perpendicular? What?
Velocity vector.
Okay, that's one of the things that we could do. We would get a velocity vector for the line, right? So, if this is our line, what's our velocity vector? If those are the parametric equations.
3, 2, 1.
Yeah, 3, 2, 1. Okay? So, remember, if you have the parametric equations, look at the coefficients of your parameter, t. 3, 2, and 1. So there's our velocity. What are we going to do with that velocity vector? We've got to find the distance. We're not going to do the magnitude of v. We are going to get a magnitude at the end to get the shortest distance. How do we get a perpendicular?
90-degree angle.
Yeah.
Oh, orthogonal.
Orthogonal, dot product. Okay, we had our aha moment. Okay, we're gonna get a dot product. Remember, we found this vector PR from the point to the foot of the perpendicular. That point R was the foot of the perpendicular, and we wanted to dot that with the velocity. So 3, 2, 1. Okay. And force that to equal 0 by figuring out what t is to make that be 0. All right? So now, R. How are we going to represent the point R? There we go, with the parametric equations. 2 plus 3t, -1 plus 2t, and then 4 plus t. Now that we know that, we can get vector PR. Okay? So vector PR is the vector between the 2 points. We have the point we're coming from is 3, 0, -1. I'm going to subtract those coordinates from the coordinates of the point we're going to. So here are the coordinates of the point we're going to. 2 plus 3t, -1 plus 2t, and 4 plus t. Okay? So, the coordinates of the point you're going to, point R, minus the coordinates of the point you're coming from, point P, which we were given up here. So now we're going to simplify that and plug that into this equation that we already set up. 2 minus 3, we have a negative 1 plus 3t. Negative 1 minus 0, so that's just a negative 1 plus 2t. And then 4 minus a negative 1 is 5, so it's a 5 plus t. We're dotting that with that velocity vector. 3, 2, 1, and forcing it to equal 0. Okay? Does everyone get how we set up our equation now?
Yeah.
We good?
Yeah.
Alright, so take it from there and solve it. You guys know how to find the dot product of 3D vectors. Okay. So what do we get for our time?
0.
0. Okay. 14t equals 0, so t has to equal 0. That means that the starting point for our line was actually the closest it ever was. So when we happened to look at this thing moving along and we started the timer at time 0, that was the moment it was actually the closest to us. Alright? So that's going to be the foot of the perpendicular. Alright? So R is this point, and if t equals 0, that means our point R is what point?
Negative 1, 4.
Yeah, the starting point, 2, negative 1, 4. Okay?
How'd you do negative 1?
We went back to this generic point R that we came up with, because that was going to be the foot of the perpendicular. Okay? And then we plugged in 0 for t, because we just figured out that it's going to be perpendicular, it's going to be closest when time is 0. Alright, so that's all part A. Now that we've worked all that out, part B is relatively simple. Okay? Find the shortest distance from the line to the point. Okay? How are we going to find that actual shortest distance? What? The magnitude of which vector? R is a point.
The velocity.
PR, okay? Vector PR. So right here, we want the magnitude of vector PR, okay? Again, time is 0, right? So we have 2 minus 3 is negative 1. Negative 1 minus 0 is negative 1. 4 plus 1 is 5. So we're finding the magnitude of that vector. And in this case, it ends up equaling square root of 27. Good. Square root of 27. So that,
3 root 3.
yeah, 3 root 3. Yeah, let's simplify that. Okay, so 3 root 3 there's the foot of the perpendicular. We've got our two things. And if you think about it in an application sense, those are the two most important things in this sense, along with our time. But where is it closest, and how far away is it when it's the closest? That's really what we're finding here, guys. What's its location? How far away is it? All right. So you notice we did the same process that we were doing yesterday with 2D vectors. We just have a third component to deal with now. Okay? Now, I gave you two problems I want you to try. Both of them are odd, so the answers are in the back of the book. Okay? We're going to use the time that we've got left to get started on these. One thing I will mention here, part D on number 5 is a challenging one. Okay? Because here's the thing, we actually have two boats that are moving at different velocities. Okay? Just to graph this real quick, boat A starts at 3, -4. Okay? And it's moving -1 up 2. Okay? So here's 0, 1. Okay? Like this. Alright, so here is boat A. 2, 3, 4. Those are all times. Okay? Boat B, however, starts at what point? 4, 3. Okay? And it's moving to the left 3 and down 2. So 1, 2, 3, 1, 2. Okay? So that's at 1, and then 1, 2, 3, 1, 2, and so on. Okay? Now, if you look at this one, it's actually easy to figure out when, well, it's not easy to figure out when, but you can get an idea here because think about what we're actually finding when we're seeing when are they closest to each other. Their times matter. Okay? Look, here's their distance apart when time is 0. Here's the distance apart when time is 1. Here's the distance apart when time is 2. Okay? And if we went another 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, okay? Here's when t equals 3 and t equals 4, okay, for boat B. All right, so you have this distance apart and this distance apart. So you can see it starts out kind of long, and then kind of as their paths cross, they're getting kind of close together. All right? But you can see how the distance changes. So in here, between 1 and 2 for your time, they're probably at their closest. Over here you can see at 3 they're getting further apart, 4 they're getting further apart. So our answer is going to be somewhere around 1 or 2. Okay? What makes this a challenge is that we're not looking perpendicular anymore. We're actually going to use the distance formula. Okay? So think in terms of the distance formula. And what 2 points are you going to use? You're actually going to use a generic point using t for this boat and a generic point using t for this boat. Okay? So you don't know any definite point. Both of the points are going to be in terms of t, and you're going to use your distance formula with those. That'll give you a quadratic equation, and you need to find the minimum point. Okay? Because that'll give you your minimum distance. Okay? So try it. Try it. I bet you guys can figure this out. Okay? It's a challenging one, but I think you guys can do it. All right, so Go ahead and you can get going on that. The last 7 minutes, you could get started, at least get through A, B, and C, and then finish this up for Monday, okay?